Good afternoon, everyone. Welcome to the Monday afternoon press conference at the 235th meeting of the American Astronomical Society here in Honolulu. I'm Rick Fienberg, AAS press officer, and I'm assisted today by AAS media fellow Tharani Konchadi, who's monitoring the webcast in the back of the room. If you're on the webcast and you want to ask questions, please log into the chat room, and Tharani will relay your questions up to the front during the Q&A. I want to remind everybody to please make sure that your cell phones and any other electronics that ring or vibrate or anything are silenced. 3 press releases will be going out from NASA Goddard. They're winging their way to the AAS press list right now. And by tomorrow, we'll begin to have some of the archived webcasts from the earlier briefings up online in the webcast archive on the AAS website. So in case this is your first AAS press conference, I'll just tell you how it works. I'll give a brief introduction, introduce all the panelists and their topics, and then we'll have all the presentations one after the other, and then when it's all finished, we'll have time for questions and answers, assuming that the speakers keep to time. All right, so this is, I think this might be the 3rd press conference that we've had at a AAS meeting about TESS, NASA's Transiting Exoplanet Survey Satellite, but it is the only the 2nd one where science results have been presented. The first was a preview of the mission right before launch, but things are really rolling with the mission now, and so I'm very excited that we're going to have a whole panel devoted to multiple interesting discoveries coming from TESS. We're going to start with Emily Gilbert from the University of Chicago. She's going to speak on a new discovery of a compact TESS multiplanet system. She'll be followed by Joseph Rodriguez from the Center for Astrophysics, Harvard and Smithsonian, on Spitzer observations of a habitable-zone planet from TESS. Gabrielle Engelmann-Suissa from NASA Goddard will follow with exploring habitable-zone Earths in synchronous rotation around cool stars. And then Veselin Kostov from NASA Goddard also, the first circumbinary planet discovered by TESS. Finally, a dance with dragons. TESS reveals Alpha Draconis is a detached eclipsed binary. That'll be from Angela Kochoska from Villanova University. And then, last but not least, Paul Hertz, the director of the Astrophysics division at NASA headquarters, will offer some closing comments. And with that, I'll turn it over to Emily.
We're still loading. Okay. Hello, everybody. My name is Emily Gilbert. I'm a PhD candidate at the University of Chicago, and I'm here today to talk to you about an exciting new system of planets we found using TESS. These planets are around the star TOI 700, which is a nearby bright M-dwarf star, and it has 3 known transiting planets. The outermost planet, TOI 700d, is TESS's first habitable-zone Earth-sized planet. So a little bit of background before I begin. TESS is the Transiting Exoplanet Survey Satellite, shown here. TESS is an all-sky survey that launched in April 2018, and it is set to observe over 200,000 stars in 2-minute cadence over its nominal 2-year mission. TESS observes the sky in sectors for 27 days, with 13 sectors per hemisphere. TESS started observing in the southern hemisphere before flipping and observing the northern hemisphere, as you can see here. The way that TESS detects planets is via the transit method. So the way that this works is that you measure the brightness of a star over time, and if a planet passes between you and the star, you'll see a dip in the amount of light that you receive. So here you can see a composite image of the first year of TESS observations made by Ethan Cruzy of NASA Goddard. TESS's continuous viewing zone is shown here in the blue circle, and TOI 700 is in the constellation Dorado, pointed here in pink. Because TOI 700 is in the continuous viewing zone, TOI 700 was observed in 11 of the first 13 TESS sectors. Some background about the host star. TOI 700 is an M2 dwarf star. Its mass and radius are each about 40% the size of the Sun. We estimate that the age of the star is over 1.5 billion years, as the star is quiet and has a rotation period of around 54 days. And the star itself is just over 100 light years away. So the first planet in the system is TOI 700b. This planet has an orbital period of 9.98 days, a radius of 1.01 Earth radii, and at this radius, we estimate that the planet is probably rocky. At TOI 700b, it receives 5 times more starlight than the Earth receives from the sun. The next planet in the system is TOI 700c. It has an orbital period of 16.05 days, a radius of 2.63 Earth radii, and is probably gaseous, similar to Neptune. The light from the star is about 2.6 times more intense than the light from the sun at Earth. And now I'm very excited to introduce TESS's first habitable-zone Earth-sized planet. TOI 700d has an orbital period of 37.43 days, a radius of about 1.2 Earth radii, and we think that this planet is probably rocky. At the location of TOI 700d, the light from the star is about 86% the light that Earth receives from the sun. With this amount of light, TOI 700d is within the star's habitable zone. Because this system is close and around a relatively bright star, TOI 700d is one of the best-known small habitable zone targets for additional follow-up. This includes characterizations such as radial velocity measurements to determine planet masses. TOI 700 is a multi-planet system, and the fact that there are multiple planets allows us to study the system dynamics. We ran a stability analysis, and we showed that the system is very stable. We also conducted a photodynamical analysis, which allowed us to place constraints on the planet masses and densities, and also showed hints of transit timing variations. So here's the full light curve from TESS, the first year of observations. You can see each of the 11 sectors is plotted in a different color with the small dots. The planet transit depths are marked in blue, pink, and purple, and the big dots underneath mark where TESS was able to observe a transit. In addition to the TESS observations, we conducted many ground-based follow-up observations in order to fully vet the system. So this includes high-resolution imaging, ground-based spectroscopy, and ground-based transit observations. We also ran the software packages Dave and Vespa in order to rule out false positives and statistically validate the system. But because TOI 700 is such an exciting target, we wanted to be absolutely sure that the signal was real. So in order to do this, we confirmed the transit using Spitzer, which you'll hear more about from Joey in a second. And just to wrap up, I'd like to thank the approximately 100 co-authors we had on this paper. A special thanks to each and every one of you for this amazing group effort. Thank you very much.
All right, good afternoon, everyone. I'm really excited to be here. I'm Joey Rodriguez. I'm an astronomer at the Smithsonian Astrophysical Observatory, working at the Center for Astrophysics, Harvard and Smithsonian. And today I'm going to talk to you about how we use Spitzer to confirm the first habitable zone Earth-sized planet from TESS, TOI 700d. So in the previous talk, we heard about this incredible system of 3 planets orbiting a small dwarf. And what's really interesting about this system is TOI 700d, the outermost planet, because it resides in its habitable zone. And so given the nature of this discovery and that it's the first habitable zone Earth-sized planet from TESS and the expectation of investing a lot of resources for the detailed characterization of this planet, we wanted to be absolutely sure that this was real, as well as really refine our understanding of the planet. And so we proposed for Spitzer discretionary time on Spitzer to confirm to confirm 2 transits of this system. So the Spitzer Space Telescope is really well suited for this observation, mostly because it's much bigger than TESS, and it has about 64 times the collecting area that TESS does. And the real purpose of this observation was to really rule out any last remaining false positive scenarios and confirm TOI 700d as a bona fide planet. And we were actually awarded 2 transits, with the first one on October 22nd, and this was PI'd by Dr. Andrew Vandenberg. And just to give you a sense, this is what TESS would look like in scale to the image in the background of Spitzer. And you can see that Spitzer is much, much bigger, and that is really why it's so well suited to this observation. Also, just to quickly remind you that both Spitzer and TESS are observing transits of this planet. And so as a planet goes around its star, if the line of sight is correct, it will block out some of the light periodically, and that really tells us how big the planet is. Now, before I get into Spitzer observations of TOI 700D, I wanted to mention that we also got follow-up observations from the ground from the Las Cumbres Global Observatory Network, the LCOGT, on TOI 700C, which is the mini Neptune at 16 days. And so at the top here, you are seeing the light curve of TOI 700C from TESS. And at the bottom, that is the observation from the ground from the LCOGT telescope. And so this allowed us to refine our understanding of TOI 700C and really improve our confidence on the parameters, specifically the radius and the period. But the main point of our proposal was to observe TOI 700D, TESS's first habitable zone Earth-sized planet. And at the top here, I'm showing you the light curve of TOI 700D from TESS. So this is all 11 sectors. And at the bottom, wait for it, you will see the transit from Spitzer on October 22nd, which was confirmed that the transit was not any kind of a systematic, and it really allowed us to refine the parameters of the planet, specifically improve our confidence on the radius of the planet and the period, which will be very useful for future follow-up. Now, the key question that still remains is this planet rocky, like the terrestrial planets in our solar system, or is it really more like a mini version of Neptune, which really would not be hospitable for any kind of life? And the only way that we'll really be able to go forward and understand this is to get radial velocity measurements and measure the mass of this planet, and therefore understand what the bulk composition is and whether it's consistent with rocky or not. And to do that, we need radial velocities. And just to quickly overview, the radial velocity technique or the Doppler technique or the wobble technique is simply that as a planet orbits its star, the star will actually orbit the center mass of the two bodies, and therefore the star will appear to wobble. And so we can actually measure that velocity shift or that wobble, and that tells us directly how massive the planet is. And to give you a sense, for TOI 700D, the planet tugs on its star with a velocity of about 80 centimeters per second. What's really interesting is that is very similar to the speed of the fastest ground-based turtle, Birdie, from the Guinness World Records. And Birdie ran an impressive 28 centimeters per second, so very close, within a factor of 3 of what the orbital velocity, the induced velocity on the star would be. So how well suited is TOI 700D for this observation? Well, on this plot I'm showing is the planet radii of all small planets under 4 Earth radii versus the light received on the x-axis relative to the Earth. And so quickly we can say, let's remove all planets that are too hot to be habitable. Let's remove all planets that are too cold to be habitable. And let's remove planets that are just not Earth-sized and therefore too big for the study. And what we're left with is about 10 planets. And the size of the dot actually indicates how accessible an RV measurement would be. And as you can see, TOI 700D is the largest point in this parameter space of this plot, and therefore it is the most accessible target for RV measurements for the habitable zone Earth-sized planets known to date. And just to give you a sense, this is where the Earth would be on this plot. So with that, I just want to put up my contact information, thank all of the co-authors. We didn't have 100, but I think we had about 45, 50. And just make a mention that we actually observed a second transit of TOI 700D yesterday. I was a little upset that it wasn't today. And it actually, we're hoping to get that data and include it into the actual final paper. So thank you for your time.
Hello, everyone. My name is Gabrielle Engelmann-Suissa. I'm a researcher at Goddard and USRA. And today I'll talk to you guys about how we modeled potential atmospheric conditions for the new exciting planet TOI 700D. So a brief recap of the properties of this planet because it informs our modeling. It is a planet in the habitable zone that is Earth-sized around an M star. So we expect it to be tidally locked so that one side of the planet always faces the star. TOI 700D receives 86% of the starlight that Earth receives from the sun, so it is in the habitable zone. So we modeled potential atmospheric conditions, assuming that this planet has an atmosphere and that it is rocky. We use 3D models, or general circulation models, GCMs, because tidally locked planets have 3D circulation effects that can only really be properly captured by 3D models. These 3D models can tell us how cloudy could the atmosphere be, how hot could the surface be, how much water vapor, and in my opinion, the most important thing, what observable signals could we detect from this planet? So we conducted a simulation grid for potential climate states for this planet. We explored planets that are completely ocean covered or completely land covered. We explored different atmospheric compositions, such as modern Earth-like atmospheres or atmospheres like 2.7 billion years ago on Earth, called Archean Earth-like atmospheres with more CO2 and methane, and early Mars-like atmospheres, which are CO2 dominated. We also explore atmospheres that have different atmospheric pressures, so denser than the ones that we experience here on Earth. Across the board, we find around all of our 20 simulations that TOI 700D is a robust candidate for habitability. It maintains liquid surface water in our simulations, and in none of our simulations does the planet go into a runaway greenhouse state like Venus. So now we can take these models and synthesize observables so we can simulate what we could see with them using transmission spectroscopy. Transmission spectroscopy is when light from the star interacts with the atmosphere of the planet and interacts with the molecules of the atmosphere and gives us spectral features that indicate the molecules in that planet's atmosphere. So one of the examples of our simulations is a land-covered modern Earth-like atmosphere. You can see here that the day side has high temperatures and the night side is very cold. There's a stark difference between the day side and the night side. The winds are circulating to the center of the day side because of this planet's rotation. The average global surface temperature of this example is -40 degrees Fahrenheit. So if you can survive in Chicago, then perhaps you'll be okay here. And we also, again, synthesized the spectrum for this planet if TOI 700D was this type of planet. And here it is. We can see CO2 and methane features. This spectrum shows that these features are relatively small. We can not only do transmission spectra, but also we can synthesize phase curves. So as the planet is rotating in its phases, think of the moon's phases, we can see how much thermal emission is being given off. So you can see the day side is very hot, and then the night side is very cold, and the day side is very hot again. And that's because there's no water vapor. It's a land-covered planet. There's no water vapor in the atmosphere that can transport heat. Another simulation example that we did was a dense ocean-covered CO2-dominated atmosphere. So by dense, we mean think of 40 meters under the ocean. That's the type of pressure that would be on the surface of this planet. There's so much CO2 in this type of simulation that heat is transported all around the planet, and it's hot everywhere. But again, it still maintains liquid water. And we synthesize a spectrum for this planet as well. And you can see there are CO2 features, but these features are very small, and that's because this planet is so hot that many clouds are in the atmosphere. So those are two examples in our simulation grid. So what did we learn from this modeling? We learned that a lot of the signals that are necessary to actually characterize the atmosphere of this planet are low. So although telescopes like James Webb would not be able to characterize the atmosphere of this planet, this will hopefully motivate technological advances needed to detect these signals, so that one day when we do get the opportunity to characterize the atmosphere of this planet, we can compare it to our models to see what kind of atmosphere it is. So no matter what, this planet, this very interesting planet, is always going to be a very different place like Earth because it's in a very different environment than Earth. So I'm really excited to see what we can learn next about this planet. I'd like to thank all of my collaborators. Thank you very much.
Okay. Hi, everyone. I'm Veselin Kostov. I'm an astronomer at NASA Goddard and SETI Institute. And now I will take you from a planet, from a system with 3 planets and 1 star to a system with 2 stars and 1 planet, and share some of the highlights of our recent discovery of the first circumbinary planet from TESS, TOI 1338. First, to make sure that we're all on the same page, let me briefly introduce what a circumbinary planet is. Is the animation running? Yes. Using this beautiful animation from Chris Smith from Goddard, Circumbinary planet is a planet orbiting 2 stars. We have 2 stars in the center of the system here. You can see the large and the small star in the center. And there is a planet orbiting outside the orbit of the 2 stars. It's a circumbinary planet. For the case of 1338b, the configuration of the system is such that we see both transits of the planet across the primary star, just as we saw here, as well as stellar eclipses. Eclipses are when the 2 stars block each other's light periodically from our perspective. And if we measure the brightness of the system as a function of time, we are going to see something like the plot on the bottom of the figure here, where the features in red are the primary and secondary stellar eclipses. There is a clock ticking in the center of the system, the clock of the stellar eclipses. This happens every 15 or so days for the system, and every about 95 days we detect transits from the planet itself. These are the 2 highlighted in green. And here's the actual TESS data. The upper panel shows the brightness of the system as a function of time, as a function of days. This is about 300 days of TESS data. It was observed in 12 sectors of data. The deep features here, you see these are the primary eclipses when the small star blocks the big star, again from our perspective. And highlighted in green are the 3 transits of the planet. It transited the primary star 3 times during the mission. You can see them zoomed in on the bottom 3 panels. Interestingly, transit number 3 was first noticed by a high school intern at Goddard a couple of days after he started working on this project, so this was pretty lucky for him and for all of us. We're not that lucky usually. Now, finding these planetary transits is, of course, the first step. Next, we need to make sure that they're real instead of false positives. And to demonstrate this, here I've shown a 20-day section of the light curve of the system. This is sector 3 of TESS data. You can see the prominent primary eclipse right in the center of the light curve. This is when the small star blocks the big star. You can see 2 secondary eclipses highlighted in purple when the small star goes behind the big star. 1 planetary transit highlighted in green. And a large number of things that look like transits but are unfortunately data artifacts. Unfortunately, these artifacts very often look like transits, so we need to be really careful when we analyze the data. Basically, what we do is we go through the light curve. Is this real? No. Is this real? No. Is this real? No. Oh, man, is this real? Yeah. So, and then we keep going through the entire light curve. And next, just as Joey described, we use radial velocity measurements, but in this case for the 2 binary stars in the center of the system. Here you can see the radial velocity measurements for the primary star from Corley and Harp's spectrograph. Luckily, the system was observed long ago, long before TESS, and it was confirmed to be an eclipsing binary before TESS as part of the EBLM project. And there is a very extensive archive of radial velocity data, which really helped with the analysis of the system. Compared to the radial velocity signal that Joey mentioned, here we're talking about kilometers per second instead of centimeters per second. We have 2 stars pulling and pushing each other. Now, like the case of Earth, the orbit of the planet precesses from our point of view. Unlike the case of Earth, this precession effect is much more pronounced because we have 2 stars in the center of the system instead of 1. So both stars are pushing and pulling on the planet. And the result of this is that the orbit tumbles so much, and you see this tumble in the animation here, that sometimes the planet just doesn't transit at all from our perspective. This is a very typical feature of transiting circumbinary planets. And here you can see what we call the orbital evolution of the orbit of the planet in terms of how far away the planet from the primary star is from our perspective each time it crosses the line of sight as a function of time. The sinusoid here, this is the precession of the planet. It precesses every about 22 years or so. And transits are observable from Earth only within this green band in the center, so for about 1/3 of the precession cycle. And overall, transiting circumbinary planets produce transits at different times from different locations of the sky. So it just so happened that TESS observed this system at this particular time and detected the transits. And just to briefly put TOI 1338 into context, here you can see the sizes and orbital periods of the planets detected from Kepler in green circles, TESS in orange triangles. The blue squares here represent the 12 circumbinary planets we discovered from Kepler. The magenta triangle is TOI 1338b. This is the 13th circumbinary planet. It is similar in size and orbital period to those we discovered from Kepler, and it is an exciting new start for circumbinary planet potential of TESS. So if you're interested in circumbinary planets, stay tuned. So with that, I would like to thank you, and of course, know that it is just me standing here, but this is a very large team effort from a large number of people, so thank you all.
I'm still waiting here. Okay. Hi, everyone. My name is Angela Kochoska. I'm a postdoc at Villanova University. And I won't be talking about planets, but I'm here to tell you how TESS helped discover that Alpha Draconis, a well-known, well-studied, and nearby star, is in fact an eclipsing binary. So Alpha Draconis is an interesting star and made its first mark in history as being a North Pole star. As you know, Earth's rotational axis wobbles or precesses with a period of about 26,000 years, and during that time, the direction of the North Pole draws out this orange circle that you can see on the image here. Well, coincidentally, Alpha Draconis falls right on this circle between the 4,000 and 2,000 mark, which makes it the North Pole star from the 4th to the 2nd millennium BC. A little bit more information on the star itself. It's a bright star at a magnitude of about 3.68. It can be found at a distance of 270 light years from us. It has also been used as the standard star for its spectral type, A30, and shows uncharacteristically high abundances of mercury and manganese in particular, which makes it a chemically peculiar subgiant star. Since the early 20th century, it's also been observed as a single-line spectroscopic binary, and here you can see its radial velocity curve. This means that we can only see the Doppler shifts and the wobble in the spectrum of the primary, but we can't really detect the secondary in the spectrum. From this, we can derive some parameters of the binary system itself, like the period, which is about 51.4 days, and the eccentricity of 0.43. Recently, interferometric studies have been able to resolve the secondary as well and measure its brightness and showed that it's about 5 times fainter than the primary. Here's Alpha Draconis in the TESS viewing field in sector 14, 15, and 16, circled in blue. And you might be wondering why we decided to look at TESS data for this star in particular. Well, in addition to all of these interesting stars that I mentioned about, all of these interesting things I mentioned about the star, it's also been suggested that it's photometrically variable, meaning that it changes in size periodically or pulsates, which can then be detected in changes in the brightness. Unfortunately, we haven't been able to detect any evidence of these pulsations in TESS data, but by looking for them, we found something even more exciting, for me at least, and that is eclipses. So here's a primary eclipse observed in sector 14, a secondary in sector 15, and another primary in sector 16. And you might be wondering how we could have missed this, since it's been known for almost a century that it's a binary star. Well, there are two things. First, the eclipses are pretty narrow. They all last about 6 hours, so they're very easily missed from ground-based observations. But also, this is a very bright star that can easily saturate the detectors of space-based observatories like Kepler, for example. So TESS was really in a prime spot to detect this for the first time. Why is having the light curve important and exciting? Well, first, just analyzing the light curve itself, we can get a lot of information on the system and the stellar components. We can get estimates on the fractional radii of the two stars, the inclination of the system, the surface brightness ratio of the stars, the eccentricity, and in some cases, the photometric mass ratio. But not only that, if we combine this with the existing radial velocity measurements, which can constrain the semi-major axis, and the mass ratio, if it's a double-lined spectroscopic binary, we get absolute values for the fundamental stellar parameters, like masses, radii, and luminosities. So we did exactly that. We took the TESS light curve and the radial velocity curve, and this is our preliminary model of the system, very preliminary. But you can see that in addition to the period and eccentricity, which we knew before just from the radial velocity curve, we now have estimates on the semi-major axis, which is about 0.4 astronomical units, the inclination of the system of 87 degrees. But not only that, we now have preliminary estimates on the stellar parameters as well, like radii and temperatures. So the primary star has a radius of about 4 solar radii. The secondary we estimate as at about 2 solar radii, and the individual temperatures are 10,000 and 8,000 degrees Kelvin, respectively. So our work is very far from done. Currently, we're collecting ground-based follow-up spectra from the SONG spectrogram, and we'll be trying to look for the secondary contribution and refine our element abundance analysis. We're also hoping to include more TESS and Gaia data to better constrain the parameters we're modeling. But more importantly, this discovery shows that TESS is not only useful for detecting and characterizing exoplanets and can be used for a lot more exciting astrophysics as well. So our aim is to look for more of these bright detached eclipsing binaries with TESS and model them to better constrain the fundamental stellar parameters to a level of accuracy that can be preceded. Thank you.
My name is Paul Hertz. I'm the director of astrophysics at NASA, and I have no slides. When TESS was proposed, excuse me, when TESS was proposed to NASA by principal investigator George Ricker of MIT and his team, there we go. He showed us a mission that would survey the sky looking for the closest and brightest stars with transiting exoplanets. And these would be the best targets to follow up with NASA's telescopes like Hubble and Spitzer and the upcoming James Webb Space Telescope. And now that TESS is halfway through its second year, it has certainly demonstrated the power of its proposed science with discoveries of thousands of potential exoplanets. But the power of TESS goes far beyond discovering exoplanets, and with its ability to make time-lapse 30-day movies of every sector of the sky, it's a premier observatory, a premier astronomical science machine that allows us to study every twinkling object in the sky, and is being reported at papers and posters throughout this meeting. It's giving us a new look at the life cycles of stars, at comets, and other cosmic objects. And I'm incredibly excited about these discoveries from TESS. The breadth of these findings shows us that the first year and a half of TESS observations is just the tip of the iceberg for what this amazing science machine can accomplish during the life of its mission. This is the last month of observations for the Spitzer Space Telescope, one of NASA's great observatories, our infrared great observatory. And so it seems fitting that one of these science discoveries today should have been confirmed by Spitzer. Spitzer was also the satellite, the telescope, which discovered the 7 Earth-sized planet and the TRAPPIST-1 planet. And now it's helped us confirm the first Earth-sized planet in the Habitable-Zone that was discovered by TESS. Just 20 years ago or so, as you may recall, we did not know whether exoplanets were common or rare. And we now know that pretty much every star in the galaxy has exoplanets, which makes a mission like TESS both doable and scientifically productive. So now that we know that exoplanets are out there, TESS is honing in on those stars in our own galactic backyard that have transiting exoplanets. And we've seen today some of the exciting exoplanets that TESS has discovered. I'm sure it will be discovering more, and I can't wait to see what TESS discoveries we'll be talking about at next year's AAS meeting. Thank you.
Well, you did keep to time. That's very good. All right, so we're going to take questions from reporters in the room first. Actually, anybody in the room, although I tend to favor calling on reporters. Raise your hand. Let's see, we got a microphone, or we're about to have a microphone. Wait for the mic, identify yourself, and tell us who you write for. And then if you're on the webcast, log into the chat and queue up your questions, and Tharani Konchadi will relay those to us when we get an opportunity in a few minutes. So we'll start down here with Alex.
Thanks. I'm Alexandra Woodsey with Nature, and my question is for Emily Gilbert. Can we talk a little bit about habitability, habitable zone, Earth size, Earth-like? Nobody said Earth-like, which is good, but can you talk about what you mean by habitable zone and what that means in terms of habitability in the public concept of what habitability means?
Yes, okay, that was a lot of questions, and there's a lot of landmines that I'm going to try and avoid here. So when we talk about Earth-sized, we know that the planet is 1.2 Earth radii. We get that from TESS. But right now, as has been mentioned in a couple of the talks, we don't know the mass of the planet. And so if we can measure the mass of the planet, we combine the mass of the planet with the radius of the planet to calculate the planet density. And so this then lets us compare to models, and we can estimate the composition of the planet. So right now, we only have a piece of the puzzle. This is why everyone was very careful to not say Earth-like, because we don't know entirely what it's like. And then a little more in the area of the research that I do, I study M-dwarf stars. And so this type of star is very different from the sun. So it's a smaller, cooler, redder star. It's significantly more active, and it's more active for longer into its lifetime. And so this means that the planets are subjected to a much stronger radiation environment. And because the star is cooler, the habitable zone planets, so okay, another one of your questions, habitable zone is defined as the region where you could feasibly have liquid water on the surface of the planet. So not too hot and not too cold. Our papers should actually be appearing on arXiv in the next half hour, 45 minutes or so. So you can refer to those, but we use the Koperapu definitions of the habitable zone. And so because the star is cooler, in order for planets to be in the habitable zone, they have to be much closer into the star. So this means they're subjected to significantly more radiation than habitable zone planets around a star like our sun. I think I got most of your questions in there.
Okay, Gilbert, down here, and then we'll go to the back.
Govert Schilling, freelance from the Netherlands. This is in addition to Alex's question. You said the planet receives 86% of the sunlight that the Earth receives from the sun. So I was wondering why you put it on this next graphic on the very inside of the habitable zone of this star.
Yeah, so the Earth is actually closer in. It is just barely in the habitable zone of our own solar system. So it's not actually smack in the middle of the habitable zone.
Okay, any more questions here in the room? Okay, we'll take one in the back. And then I saw one over here. Who's that? Okay, two, okay.
So I had a question for Emily and Joseph. It seemed that the light curve...
Could you identify yourself, please?
Yeah, Bill Diamond from the SETI Institute.
Thank you.
The light curves for the exoplanet from both the Spitzer and the TESS observations had similar features at the bottom of the curve, and I was wondering if that was, an artifact of the data or if there's something real to that.
So we think it's an artifact of the data, and so the second Spitzer transit that was observed yesterday will really allow us to understand those systematics and really probably help us understand the noise, but we don't believe that mid-transit brightening that we see is a real event. And we do believe that to be a systematic.
Okay, so we have two down here. We'll start with Liz and then come over to Christine, right?
Hey, Liz Landau from NASA. Emily, I had a question about tidal locking. I wonder if you could explain to us why you think that this planet is tidally locked to its star.
Yes. So in order to calculate the time for tidal locking, you need to make a lot of estimations about planet and star parameters. But we ran a calculation, you can see more about this in the paper, and we estimated that the timescale for tidal locking was on the order of several million years. And so because we know the age of the star is over 1 billion years, we assume that at this point in time that the planet is tidally locked.
Okay, Christine?
Christine Pulliam from the Space Telescope Science Institute. My question is for Gabrielle. And so you modeled the expected spectra of these planets, in particular the one in the habitable zone, but you said that they probably, or it probably wouldn't be a good candidate for James Webb. Why is that?
Thank you for your question. So most of the spectral depths are below 10 ppm. And so every telescope that we send up to space has a noise floor, and although we don't know the noise floor of what James Webb is until we actually launch it, estimations of the noise floor is from 10 ppm to 20 ppm, so basically the spectral depths are lower than the noise floor below which we can't see anything.
Tharani, do we have any questions online?
Yes, we have a question from Erica Carlson, reporting for Discover and Astronomy magazines. This question is directed at Dr. Kostov. Does the discovery of TOI 1338b tell us anything about how many more circumbinary planets TESS might find? And what kinds of questions will these systems help answer?
Good question. So first it tells us that TESS can do that. And remember that TESS is 10 times smaller than Kepler. So, and we discovered these transits by eye. Each of them we need to see them by eye. So TESS is sensitive enough to do that. And our estimates are on the order of 100 new planets. We expect to see about 100 new circumbinary planets from TESS. Where do I look when I talk to people online?
Why don't you look to the questioner?
Okay. What was the second part of the question? Oh, yeah. So as I mentioned, we have a handful of systems known so far. We have 12 systems now, 13. So you can imagine that drawing general characterizations for these types of planets is a bit premature yet. Most of the planets that we know, I would say all of them are large, all of them are on longer orbital periods, so they're kind of similar to each other. What we're looking for is we want to see different and new systems, and TESS will allow us to do that. And TESS is the only instrument who is going to allow us to do it in the coming future. Does this make sense?
We've all agreed it makes sense. Anything else online?
No, that's it.
Okay, any more questions in the room? Okay, we'll take one from Jeff.
Jeff Faust, Space News. It's for Joey Rodriguez. If you discover something like TOI 700D, some other one like that, next month, and you don't have Spitzer available to help confirm it, what's the plan B to be able to confirm its existence and better define its orbit and size?
So I think just state immediately, you know, that just shows the power of what Spitzer was able to do and what Spitzer's been able to do over, you know, the last 10, 20 years. The short answer is the options are a bit limited because of how shallow the signal is, but the recent launch of the KOPS mission may allow us to actually observe another transit with using that facility. It really will depend on what the size of the transit is that we discover for the next, say, TOI 700D. But that's one facility that we can go forward and try to do this type of observation with. But it is a bit limited without Spitzer. I think that's a key thing to make clear.
Oh, very good. Okay, we'll take one over here from Ray, and then we'll go to you. All right?
Ray Villard, Space Telescope Institute. Is there anything that Hubble can do looking at these this one you just reported today in terms of transit photometry?
We haven't thought about our Hubble proposals yet.
Yeah, it's one of those questions. You know, we'll give you more detail maybe in March. And you know, Gabby really summed up that atmospherically, no, there's not much we can do. Obviously, with James Webb, yet alone Hubble, but there are things that we can do to say characterize the host star a bit better with Hubble. What those will be, stay tuned, and we're going to figure those out over the next few months and try to put in proposals.
Okay.
Yutanos from CU Boulder. I have a question about the circumbinary planet and how these circumbinary planets are formed. Are there any ideas?
Can you repeat the question?
Are there any ideas on how circumbinary planets are formed?
How they're formed.
Yeah, thanks. He's the expert in the field here. No. So, so they form as planets around single stars. Beyond certain distance from the star, the disk is not that much different. The protoplanetary disk is not that much different from a disk around a single star, but you need to be further away. So they form as typical planets.
We'll come back to Christine.
Thanks. Christine Pulliam again from STSI. Another quick question for Gabrielle. Your animation triggered this question, and I was wondering, you calculate the temperature on these planets, or on the habitable zone planet. Do you also estimate a wind speed? And if I want to build a house in the terminator zone, does it need to be hurricane proof?
Yes, the winds are accounted for in the 3D models. I don't know anything about building houses. So.
Tharni, do we have any more online?
Nope, nothing.
All right, great. That gives me an opportunity to ask a question or two. For those of you who are on the webcast, it's Rick Fienberg from the AAS. So my first question is for Emily. I think you mentioned that you are seeing hints of transit time variations in the multiple planet system, and I was curious, are those consistent with coming from the known planets, or is there an implication that there are additional planets in the system?
So as of right now, we believe it's just the 3 planets in the system. We didn't see any evidence for additional planets outside of that. There are, of course, mass constraints on that analysis, so smaller planets would induce smaller signals, so those could potentially be hiding further out. One thing that was really interesting, actually, that I didn't mention is that planet C is inclined relative to the plane, so there could be other planets in the system that are more inclined and aren't transiting. One thing we do hope to do is look at the next 11 sectors of TESS data, so when TESS starts observing the southern hemisphere again in July, we'll receive 11 more sectors, so we can look at that and further our dynamical analyses.
Okay. Does that mean that, that the mission, that we know we're going to, after we finish the northern hemisphere, we're going to go back to the southern?
Yes, that's planned.
Okay. Let's see. I wondered, Ray was just asking about what Hubble might be able to do, and I was wondering if, this I think is for Angela, whether now that we know that Alpha Draconis, Thuban, is an eclipsing binary, do you think Hubble can get, can help refine, what you're learning about the two stars? Is it capable enough to I guess it can't split the stars, right? Because they're too close together? Or do you think it could?
We already have interferometric studies that have been able to split the two stars and involve the secondary. But what we're most interested in getting right now is the spectrum of the secondary star. The TESS light curve is good enough to get us radii and temperatures, but to get the masses, we're looking for the secondary radial velocity curve, which can constrain the mass ratio. So we haven't thought about Hubble yet, but maybe we'll try to think about that still.
And a question for Paul. Since you brought up the fact that Spitzer will be winding down its mission in January, can you just remind us why that's the case? Is it a question of funding? Is it a question of exhausted consumables or something else?
In the 2016 senior review, the Spitzer final plan was approved, and the end of the Spitzer mission leads into the James Webb mission. So we've been planning towards this end of mission for over 3 years now. We've extended it several times from the original extension. It is true that operations are getting more difficult as Spitzer drifts further and further away from the Earth. Communication and data download are difficult, but even more importantly, thermal control is more difficult because of the Sun-Earth-Spitzer angle. But it isn't impossible to operate it a little bit longer. Nevertheless, we have carried out the plan that we made 3 years ago.
Okay. Any other questions from here in the room? Okay.
Hi, Joshua Schlieder from NASA Goddard Space Flight Center. There's a lot of discussion about TOI 700D being a small planet in the habitable zone, and prospects for follow-up don't look super promising. But I wanted to ask about the other two planets in the system. What prospects are there for TOI 700B and C?
In the sense of radial velocity observations, as I discussed for TOI 700D, there's all three planets will be accessible. The inner and outer planet are very similar in the amplitude, but the middle planet is on the order of a few meters per second, and so that we'll probably get that first. In the sense of characterization, I think there's a lot that we can do with the middle planet, which is probably a mini version of Neptune, and maybe even possibly peer into the atmosphere of that planet, especially with James Webb. So I think we've been kind of clear that James Webb may not be able to do much for TOI 700D, but I think there's a lot of prospects that it can do stuff for TOI 700C, and maybe we can learn about D from what we learned from C.
Any other questions come in online?
Oh, nothing.
Okay. Well, in that case, we'll wrap it up a few minutes early. I want to thank our panelists again, and I want to thank my colleagues in the Public Information Office, Jeanette, Frank Reddy back home, Claire Andrioli, for helping to put this panel together. And I want to thank all of you for coming. This is, I think, our best turnout so far, which is great. We are only barely halfway through the press program for this meeting. There's still 2 full days ahead. The next press conference will be tomorrow morning at 10:15. It'll be 4 presentations on the Milky Way inside and out. So thanks again, and we'll look forward to seeing you tomorrow.